Hello, greetings to you all, and I'm here with another exciting video on applied electronics IoT. Yes, so today our goal is to cover the reading section of page 32 to what? To 36. So my goal is to summarize page 32 to 36 IoT. Then it will help you to what? To solve the questions. So it's going to be a short video. And once you are done watching it, please, once you get the understanding of it, take your time, read it, and solve the questions at the end of the chapter. So you are going to solve the questions at the end of the chapter. The questions are located at page 39 to 41. So we are going to complete the semiconductor materials and other stuff today, right? So once we are done, you read page 32 to 36, then you try your hands on that question. I told you applied electronics is more like reading. You get it? And the questions that they are going to set in the exam, based on the previous questions that have been seen, right? It's going to be multiple choice questions, MCQs. So you don't need to rely on this video alone. This video is just to boost your desire, right? I wish to boost your desire to read the book, right? So once you read it, you get a better understanding. And once you get a better understanding, you are good to write the multiple choice questions on the final day. So please try as much as possible to read. Read everything I ask you to read, and I believe that you are going to be fine. Okay, so as discussed last week, we plan of talking about doping of semiconductors, right? And that gives birth to what? It gives birth to the N-type and P-type semiconductor. So the doping gives birth to the N-type and the P-type, right, semiconductors. You get it? Then we talk about the depletion region. So these are the most important things we are going to talk about today. And I believe that once we are done with today's class, you will get the energy to read page 32 to 36 of the book. Then you solve the questions. Please try the questions. If you have any question to ask after completing this task, this is task 1. Let me call this as task 1, and this to be task 2. Right? You read, get understanding, solve the questions. The solution are in the book. If you have any question to ask after watching this video, you can ask me. I believe by this time you are on my Telegram page if you are watching this. If you are not on my Telegram page, I'll put the link in the description. And if you've not watched the previous video too, I'll put the link in the description as well. So try as much as possible to watch it and follow our series so that you get an A in applied electronics IoT. Yes. So let's keep the ball rolling. We are going to talk about doping. So what actually is doping, right? In my own words, right, I would say that doping is the process, right? It's the process of adding impurities to an intrinsic, right? That's the way. Intrinsic or pure semiconductor material. Semiconductor material to alter, right? To alter its properties. Thereby increasing its conductivity. There are so many definitions of There are so many definitions for doping, but this is one of the best one that you can get. So doping is the process of adding impurities to an intrinsic semiconductor material to alter its properties, right? Thereby increasing its conductivity. Actually, the impurities here can be a pentavalent element, right? Pentavalent, let me spell it well. Right? It can be a pentavalent element or a trivalent element. By this time, you should know what a pentavalent element is. So when you say a pentavalent element, there are elements that have 5 electrons. There are 5 electrons at their atomos shell, right? So there are 5 electrons at their atomos shell. And trivalents are elements that have 3 electrons, right? They have 3 electrons at their atomos shell. And the penta, right? 5 electrons at their atomos shell. So semiconductors at their pure states, they are called intrinsic semiconductors, right? They don't have any impurity in them. Once I introduce any of the pentavalents or the trivalents, then it changes its conductivity, changes its properties, right? And it makes it conduct more electrons. So when I add a pentavalent to it, I'm going to get what? A p-type and n-type. Let's analyze it. I want you to analyze it, then you get the concept. I'm not going to state it to you right now. I want us to analyze it, then we know the n-type and the p-type semiconductor. So first of all, let's talk about the n-type semiconductor, right? N-type semiconductor. Okay, very good. So what is it saying? So the n-type semiconductor is right, is an intrinsic, right? Is an intrinsic semiconductor. Intrinsic semiconductor which has been doped. We say doping. Doped with a pentavalent. I don't know why I keep on making mistake with the spellings. So which has been doped with what? With a pentavalent elements. And what are these pentavalent elements? We have phosphorus and what? And antimony, right? Example of the pentavalent elements, we have the phosphorus. Sorry. So we have the phosphorus and what? And the antimony. So these are examples. Some are also arsenic and all those. So we have these elements having like 5 electrons. So when I should draw their atomos shell, right, they have 5 electrons there. Let me use another. So let's take phosphorus. If you take phosphorus, we have 5 electrons at the atomos shell. So 1, 2, 3, 4 and 5. You get it. And silicon is having, how do you call it? Silicon is having 4 electrons. That is a semiconductor material. The semiconductor material, which is silicon, is part, and we have the germanium is also part of it. So all this was discussed in our previous video. So there's no need to hit on it again. But if I have phosphorus here, which is being doped with what? Being doped with the silicon, right? Then it gives rise to what? The n-type semiconductor. So let's explain this with the diagram. Assuming I have the phosphorus here, you get it. I have the phosphorus at the center here, and it's having, how do you call it, 5 electrons at the outermost shell. We have 1, 2, 3, 4, right? Let's say 5. Okay. So if the silicon is attached to it, use green to draw the shell of a silicon. So if a silicon is attached to this, something like this. So I have a silicon here. It's attached to it by this. Right, silicon is having 4 electrons. So let's say use different 1, 2, 3, 4. Right. Have silicon surrounding these elements. They are going to be bound with the phosphorus, okay, and we'll be having each element, right, contributing an electron to the phosphorus. Actually, they are also bounding with other phosphorus somewhere. So if I should draw a very big diagram, I have another phosphorus here, another phosphorus here. So the phosphorus is being introduced to the silicon. We have phosphorus all over, mixture of silicon and phosphorus elements. So I've just taken a portion of the diagram and I'm drawing it to show to you how it looks like. So at this point, if let's say I have silicon surrounding it, right, I also have another silicon here, then another silicon here, you get it. So we assume that since silicon is having 4 elements, right, 4 of them, right, can bond with this pentavalent element. Okay, so we have 4 at the outermost shell. So the silicon is bonding with it. So the outermost shell of the silicon, this 4 is bonding with it. But in actual sense, we need to have 8, right, on the outermost shell of the phosphorus. So at this point, since the 4 of the phosphorus has been bonded with the silicon, you get it, there will be one free electron which will be moving in the impurities hierarchy. It will be moving in the how do you call it? That's the impurities. No, impurities is not the right way, but I'll say that it is moving in the material hierarchy. So the material which is made up of silicon and phosphorus. So once we have this electron moving in it, right, it becomes a free electron. A free electron. So it moves freely into it. You get it? Because at a natural sense, let me just use, maybe someone might be confused with this. Let me just use only one element. Let me draw a phosphorus here, right? And I have a silicon at this end. I have a silicon at this end. You get it? So assuming this silicon, right, is having 4 electrons, you get it, and the phosphorus is having 5. So 1, 2, 3, 4, 5. So if we are bounding these elements, this will bond with the first one, this will also bond with this, right, this going to bond with this, then this one all the way bonding with this. So the phosphorus should have at least 8 electrons, right, at the outermost shell. So at this point, you see there was one free electron left in the phosphorus, and this electron is termed as a free electron, and thereby giving its name n-type semiconductor. Are you okay? So if you are confused with the first diagram, you can assume the second diagram as well. So the electrons at the outermost shells are bonding, right? So once they bond, there will be one free electron, right? And this gives its name, the n type, that is negative. Okay. The same applies to what? To the p-type semiconductor. So now let's move to what? To the p-type semiconductor. Okay. So what does the p-type semiconductor say? Right. So it's a type of semiconductor. It's a type of what? Of semiconductor that has been what? Has been doped with a trivalent element. So this is a type of semiconductor that has been doped with a trivalent element. And what are some of the examples of the trivalent elements? We have the boron. Boron is one of the trivalent elements, and we also have the gallium, right? So these are examples of the trivalent elements. These elements are having 3 electrons at their outermost shell. Okay. So once they bond with a silicon which is having 4 electrons at their outermost shell, a hole is created. A hole is created. So we have a hole being created. We get it. And this will give rise to the name. You see, hole is positive, right? In semiconductors, hole is considered to be positive and the electron is considered to be negative. So once a hole is created, it gives rise to what? The name p-type semiconductor. So let's illustrate this with a diagram. Okay. Let's imagine I have a boron here, right? Which is a trivalent. 1, 2, 3. Let me use 3. Okay. So we have a trivalent here, and let's assume me having 4 silicons, right? 4 silicon element being bonded with this trivalent element. So once it's being bonded with it means that this silicon also contributes but another electron here. So it already have 4. It is also bonded with other borons, right? So another silicon too is also bonded with, how they call it, the one up here, right? And it contributes an electron. You get it? It contributes an electron here. So we have 4. So we have 4 here, contributing electron with this. Then another one to be bond over here, right? And it also contributes electron to this. So we have 4 other outside. Then we have the last electron trying to bond with it. Okay. So the 4 elements trying to bond with it, but this time there is a space here. This boron, this boron needs to contribute what? An electron, right? But since there is no electron, a hole is created. You get it? A hole is created, and once a hole is created, then it gives rise to what? The p-type semiconductor is named. So you just need to understand the concepts and understand the definition. So the n-type is formed from what? A pentavalent. N-type is formed from what? Pentavalent. I keep on spelling this wrong. My God. So this is called a pentavalent IoT, and the p-type is what? It's a trivalent. So please, you should take note of it, right? They're not going to ask you to draw this on a test day. Just understand the concept behind it, and if there's any question, that's emerges out from this, you try to what? You try to answer it. So if I should talk about PN junction, right? I first have a p-type semiconductor. You get it? I have a p-type semiconductor here, which consists of holes, more holes, and few electrons. So they have more holes. In the p-type. I'm using circle as the holes, and we have few electrons, right? Let me use negative over here. So we have electrons in them, and we have holes in them too. Okay, so if I should draw the p-type also here, the n-type, sorry, let me use a different. I have the n-type 2 at this end, right? And that one to consist of more electrons, because an n-type, it has more electrons and it has some holes in them, right? And we have holes in them, so holes, right? So when they come together, a junction is created, and I want to expose you to that junction. So this junction is called PN junction. The junction here, this thin line here, is called the PN junction. You get it? This is the n-type semiconductor. So once they come together, we have the PN junction, right? And this is where the depletion layer is formed, or the depletion region. Okay, so at this point, a depletion region is formed. And how is the depletion region formed? Right, I'm going to explain to you, and you get the concept very well. So once we combine them, pay attention, once we combine them, right, because there are holes here, right, the electron begins to what? Diffuse. The word is diffuse, right? They begin to what? Diffuse into what? To the p region. That's the p-type material. Okay, so the electrons here begins to what? Move. Let me use a different marker. Let me use red. Okay, very good. So the electrons here begin to move. They are being attracted by the holes here, so they keep on moving as soon as you combine them. So they keep on moving until it reaches an equilibrium. Okay. So it moves and moves and moves until it reaches an equilibrium. Okay. So once it reaches an equilibrium, then the depletion region is formed. So once it gets to equilibrium, you have a diagram like this, something like this. You get it? Let me draw it very well here so that I get the concepts. So sketching something like this, yes. Then at equilibrium, right, you have negative at this end. The electrons will move to occupy, right, how do you call it? The holes at the p region. And we have the n region here. You get it? So the electrons, let me spell the n region well. Right. Or n-type, n region, n-type. They can mean the same. Right. So this region is the n region, and this is the p region. Right. So the electrons will move to occupy the holes at the boundary of what? Of the n region. Then once they move there, right, they create a hole. In the actual sense, electron is occupying the hole. So once it moves, it leaves the hole empty for another electron to occupy. So once it moves, it is moving to occupy another hole. You get it? So once they leave, they create holes at this end, at the boundary of the n type. You get it? Let me use positive as holes, like we discussed. So this is the n type, which consists of more holes. At this point, I will say that because an equilibrium has been maintained, the electrons will also be balanced. Okay. So this equilibrium thing can be compared with, let's say, diffusion. If you are confused, chemistry, right? The term is just diffusion. What is diffusion in chemistry? We are saying that diffusion is what? Is the movement of what? Of gases from higher concentration to lower concentration. Until what? Until an equilibrium is obtained. If you can remember that definition in chemistry, you can relay it over here. So the electrons are moving from a higher concentration, a region where there were more electrons, right? So there were more electrons and they were moving, right, to, how do you call it, to the p side. So once they are moving, there will be a point where an equilibrium will be obtained. That is, ideally, the number of electrons and the holes here, the number of electrons and the hole here are almost the same. You get it? That's ideal condition. So once they reach equilibrium, right, a hole is created at the boundary of the n type. And how do you call it? An electron is created at the boundary of what? Of the p type. And once they create a boundary like that, they form the depletion region. Depletion region. You get it? So this is what is termed as the depletion region. So at this region, a force is being created, right? At this region, let me use green. Sorry for using blue. Let me use green so that you see it clearly. So a force is created at that point. Let me use any other color. And it's positive and negative. You get it? So at this point, once the force is created there, right, it is normally termed as what? Potential barrier or barrier potential, any of them. So barrier potential or potential barrier. Some books term is as potential barrier. Others have seen barrier potential. So any of them. So this barrier potential, right, an equilibrium has been obtained. So with this one, the first image that I drew, right, was the state where the gases were being hot, diffused into the p region, right? But an equilibrium can be obtained, and at equilibrium state, you have the electrons at the edge of the p region, and you have the holes at the edge of the n region. So once that region is created, that region is termed as what? As the depletion region. So at that region, there is a force there that is preventing extra diffusion. Equilibrium has already been obtained. Let's take the chemistry here. Once the gas move from a lower concentration, a higher concentration, once the gas move from a higher concentration to a lower concentration, it will get to a point there will be diffusion, right? There will be equilibrium, right? There will be equilibrium in the room, and the gas will no longer move, but the gas will be stagnant in the room. You get it? The same way, once the electrons move, it will get to a point and the equilibrium will be obtained, and the electrons here cannot move again because we've created a depletion region, right? And that depletion region, there's a potential barrier or barrier potential existing between it, and this is more like Coulomb force. Okay. So it's existing between it, and it is preventing this electron from moving, right? So talk about diode and you will see it to be more interesting. Okay. So with the diode, this is where we have the forward bias and the reverse bias. We'll talk about it in the next video. So at this point, how do you call it? We need a force, right? We need a force, and that is normally obtained from voltage connecting to the terminals. We need a force to break this barrier potential, to break this barrier for more electrons to flow through. Right? So this is a semiconductor, a PN material, right? A PN material at the equilibrium state. Equilibrium state. So the first diagram that we drew, we saw that the electrons were moving, although we didn't see the animation, but we assumed that the electrons were moving. So once it gets to a point, the depletion region is created. And once the depletion region is created, no electron move again to the P region. And once that's happened, then a force is created between it, and this force is called the barrier potential. So please take note. It's really exciting. Just watch the video very well. If you are still confused, watch the video again. Read the book, page 32 to 36. Read it and understand the concept. If you have any question or if you have any confusion in what I've just explained, please, I've created a Telegram page. I'm not creating this video to leave you there, right? I've created a Telegram page where we discuss to see the challenges, mistakes, and everything. So if you are not part of the Telegram page, please join and share your view. If you have any question, you ask them. Silence means that you understand what I'm doing. So if you have any question, please communicate in the Telegram page. Communicate there. Send me a private message if you cannot communicate there, and I'll respond to you. Okay. So I want you to get a better understanding of this. So read the book again. I've summarized page 32 to 36 for you. Read it, and get the concept. Once you get the concept, you are good to go, right? And once you are good to go, you'll be able to pass your exams. So you try your hands on the end of chapter tests. That is located at page 39 to 41. End of chapter tests. To know that yes, you are very good with the semiconductor, right? And if any questions come under semiconductor, any multiple questions, 3 or 4 questions will come under the semiconductor, you'll be able to get a very good grade. Right? So I wish you the best of luck. Please subscribe to my channel. If you've watched this site, subscribe to my channel. Getting more people in the Telegram page. A few people subscribing to my channel. Subscribe, share to your friends. If you are benefiting from this, share with your friends. Don't hide it alone. Share with your friends. Let them also understand what we are doing here. And I believe that we'll move on. Right? Yes. The next time I'll talk about calculus. I'm trying to make more calculus videos than semiconductor, right? This is more like reading, but calculus is full of calculation. That's the reason why I like making more calculus videos. But I'll try to catch up with this. The next video, we'll talk about more simulations. We are going to move to diodes. Now, next video, we'll talk about diodes. It's going to be all diodes. It's going to be an hour video, 1 hour, promise me. We are going to do simulation, and you are going to understand everything. So I wish you the best of luck in your studies. If you meet on campus, let's just say hello and we move on. All the best.